Download this code from codegive.com, link in the description below. Implementing instant messaging solutions with Erlang, a deep dive. Erlang, with its inherent concurrency, fault tolerance, and distribution capabilities, is a powerful and well-suited language for building robust and scalable instant messaging (IM) systems. This tutorial will guide you through the process of building a basic IM application using Erlang, covering key concepts, providing code examples, and discussing considerations for scalability and reliability. 1. Conceptual overview. Before diving into the code, let's understand the core components of a typical IM system and how Erlang facilitates their implementation. User management, handling user registration, authentication, and storage of user profiles. Erlang's ETS, Erlang Term Storage, or dets, disk Erlang Term Storage, can be used for in-memory or persistent storage of user data. For larger applications, you can integrate with a database like PostgreSQL or MySQL via libraries like ecto. Connection management, managing persistent connections between users and the server. Erlang's lightweight processes, green threads, are ideal for handling thousands of concurrent connections efficiently. Libraries like gen_TCP or web frameworks like Cowboy can be used for managing these connections. Message routing, directing messages from senders to recipients. Erlang's process mailbox mechanism provides a natural way to route messages between processes. More complex routing schemes can be implemented using routing tables or publish-subscribe patterns. Presence management, tracking the online status, presence, of users. This can be implemented by having users periodically send heartbeat messages to the server. The server can maintain a presence table to track the status of each user. Data storage, optional, storing message history, user profiles, and other persistent data. Erlang integrates well with various databases. 2. Project setup and dependencies. First, let's create a new Erlang project using rebar 3. This creates a directory structure with essential files. Now, let's add necessary dependencies to rebar.config. Explanation. Cowboy a small, fast, and modern Erlang web server. We'll use it for handling WebSocket connections. Jiffy ANIF-based JSON encoder and decoder for Erlang, providing efficient JSON handling. Rulks a tool for building Erlang releases, making it easy to package your application for deployment. The Rulks configuration sets up the release process and includes sys.config and vm.args for configuration. Run rebar 3 compile to download and compile the dependencies. 3. Core modules and code examples. Let's create the core modules of our IM system. im_system_app.erl the application entry point. im_server.erl the main server process responsible for managing connections, routing messages, and handling user presence. im_handler.erl a cowboy handler for WebSocket connections. Manages individual client communication. im_user_registry.erl a module for managing user data, registration, authentication, presence. im_system_app.erl This module starts the application, launching the im_server, the main message routing process, the im_handler via the Cowboy server, and the im_user_registry for keeping track of users. An admin user is created for initial testing. im_server.erl Explanation. *start_link/0, starts the gen_server. This creates a process named im_server that will handle all the messaging logic. *send_message/3 sends a message to a specific user. It uses gen_server cast to asynchronously send the message to the im_server process. *handle_cast/2 handles asynchronous messages sent to the server. The send_message from to message cast looks up the recipient's process ID in the user's dictionary and sends the message to that process. If the recipient is not found, it prints an error message. The other handle_cast functions manages user registration and online/offline status. *init/1 initializes the server state. The state includes a dict called users that maps usernames to process IDs, and a set of online users. im_handler.url*. Explanation. *init/3, this function is called when a new HTTP request comes in. It upgrades the connection to a WebSocket connection. *WebSocket_init/1, this is the entry point for the WebSocket connection. It retrieves the username and password from the query string, authenticates the user against the im_user_registry, and registers the user with the im_server. *WebSocket_handle/3, this function is called when the WebSocket receives a message. It parses the message, assuming a simple recipient message format, and then calls im_server send_message/3 to route the message to the intended recipient. *WebSocket_info/3 handles internal messages used to register user with the server and set its state to online. *WebSocket_terminate/2 called when the WebSocket connection is closed. Notifies the im_server that the user has gone offline. im_user_registry.url*. Explanation. *start_link/0 starts the gen_server. *create_user/2 create_admin/2 creates a new user with the provided username and password, storing them in the user's dictionary. Passwords are automatically hashed before being stored. The create_admin function is used on application start to create a super user. *authenticate/2 authenticates a user by checking if the provided password matches the stored password, after hashing. *the user's dictionary stores usernames as keys and hashed passwords as values. This is crucial for security. Use a robust hashing algorithm like SHA-256 or BCRYPT. The user is authenticated based on a comparison of their past hash and the database. 4. Configuration, sys.config. Create config/sys.config with the following content. This basic configuration sets the logger level to info. 5. Build and run. 1. Compile the code *rebar3 compile. 2. Create a release *rebar3 release. This will create a_build directory containing the release. Navigate to _build/default/rel/im_system. 3. Run the server *bin/im_system console. This starts the server in a console mode. 6. Testing with a WebSocket client. You can use a browser-based WebSocket client, example simple WebSocket client Chrome extension, or uscat from npm, to connect to your IM server. *connect to ws/localhost 8080/ws, username equals user1 and password equals password. Replace user1 and password with the credentials you've registered, or the admin user. Do the same for the other user you want to chat to. Send messages send messages in the format recipient message. For example, user2 hello user2, from user1's client. 7. Considerations for scalability and reliability. The basic implementation above provides a starting point. To build a production-ready IAM system, you need to address scalability and reliability. Distribution Erlang's distribution capabilities allow you to distribute the load across multiple nodes. You can use Erlang's built-in distribution mechanisms, or libraries like libcluster for automatic cluster formation. Load balancing distribute connections among multiple IAM_server instances using a load balancer, example HA proxy, inks, or an Erlang-based load balancer. Message queues for handling high message volumes, consider using a message queue like RabbitMQ or Apache Kafka to decouple the sender and receiver. Erlang has excellent clients for these systems. Database integration for persistent message storage and user data, use a robust database like PostgreSQL or MySQL. Ecto is a popular Erlang database wrapper. Presence implementation implement a more sophisticated presence system with heartbeats and optimized storage to handle a large number of concurrent users. Message history persist messages into database. Authentication add better user authentication, perhaps using third-party OAuth to make authentication easier. Logging and monitoring implement comprehensive logging and monitoring to track system performance and identify potential issues. Use tools like Prometheus and Grafana for visualization. 8. Example of distributed message routing, simplified. Here's a simplified example of how you might distribute message routing across multiple nodes. Key changes. Node name *start_link now takes a node name as an argument. This allows you to start multiple IAM_distributed_server instances on different nodes. You would run Erl-snam node 1 and Erl-snam node 2 to start the two nodes before starting the Erlang application using rebar3 shell. User location the user's dictionary now stores the node where a user's process is running, along with the process ID, node, PID. Direct message delivery send_message directly sends the message to the recipient's process, which could be on a different node. To make this work, you'd need to 1. Ensure that your Erlang nodes are connected, using Erlang connect_node/1. 2. Modify IAM_handler.erl to use IAM_distributed_server and pass the node name. 9. Conclusion. Erlang provides an excellent foundation for building scalable and reliable instant messaging systems. This tutorial covered the essential aspects, from basic message routing to considerations for distribution. By leveraging Erlang's concurrency, fault tolerance, and distribution capabilities, you can create robust IAM applications that can handle a large number of users and high message volumes. Remember to prioritize security best practices, such as password hashing and input validation.